Welcome back to Transistor lecture series. In this lecture, we are going to explore the common emitter transistor configuration. So in this circuit, we can see that the emitter is common to input section and output section. So this is our input section, and this is the output section. So here the emitter terminal is common to both input section and output section, and we are considering the input signal applied to the base emitter section, that is input section is base and emitter terminal. So between base and emitter terminal we are providing the input signal, and from the collector and emitter terminals we are taking the output. So now if we list the set of input and output for characterization of this common emitter configuration, then we can say that input current is now IB. In previous case we have seen that input current as IE, but here in common emitter configuration it is IB. So this is our input current. So similarly output current is IC. So this is the output current, and input voltage is VBE. So this is our input voltage. So that is VBE. So if we are considering only the transistor part, and the output voltage, I'm not talking about the load voltage, I'm talking about the output voltage of this transistor. So that is VCE. So these are the four input and output parameters on the basis of which common emitter configuration may be characterized. So now if we consider the input section and output section, and if we put a resistor over here, say it maybe we may call it RB. So in that case, in input section we can say that VBB, that is equal to IBRB. So we have to put one resistance here. So IBRB, this drop plus VBE. So that is from the input section input equation we are getting, and output equation, this is the most important one, and later on we will see that lots of applications related to the common emitter configuration are based on this equation. So this is VCC, which is equal to drop across RC, that is ICRC plus VCE. So these are two important equations, and this is shown in terms of NPN transistor. Same common emitter configuration is on the basis of PNP transistor. However, this analysis is same for both of these, only the VBB and VCC, you can see that polarities are different. Now next concept is the leakage current. In common base configuration also we have seen the concept of leakage current. So if we keep the input open, that is base, if we keep open, and the current flowing through the collector and emitter, so this is the leakage current keeping base open. So it is not IC, it is a part of IC, what we call ICEO. Later on we will see that how IC and ICEO are related with each other. Now the current amplification factor of CE mode. So current amplification factor, here our input current we have seen that IB and output current as IC. So the current amplification factor, which is given as beta, so that is nothing but the change in the output current, that is IC, and with respect to the change in the input current, that is IB, where our VCE is kept constant. So this is called the current amplification factor of the common emitter mode. And in almost all the transistors, since less than 5% of the emitter current flows as the base current, therefore the value of beta is generally very high. So generally it is more than 20, and usually beta ranges from 20 to say 500. So that is a typical range of beta, and this type of connection is frequently used as it gives the appreciable current gain as well as some voltage gain we can get out of it. So next is the relation between alpha and beta. Alpha you have seen, that is the current gain in the common base configuration, and here it is the current gain, beta is the current gain of C configuration. So we have seen here beta is equal to delta IC by delta IB. So let us call it equation number 1, and we have seen that alpha is equal to delta IC by delta IE. So let us call it equation number 2. So now we know that IE is equal to IC plus IB. So which implies that if there is any change in IE, so we'll be having some equivalent change in IC and IB as well. So we can write delta IE is equal to delta IC plus delta IB. So from this relation we can further write that delta IB is nothing but delta IE minus delta IC. So now if we substitute the value of delta IB from equation 3 to equation 1, so let us call it equation 3. So from this equation to this equation, if we substitute the value of uh, delta IB, so what we obtain that beta is equal to delta IC divided by this one delta IE minus delta IC. So now if we divide the numerator and denominator with respect to delta IE, what we obtain delta IC divided by delta IE, and here we'll get this, for this portion we'll get 1 minus delta IC divided by delta IE. Now what is this delta IC by delta IE? This is nothing but our alpha. From equation 2 we can find this is nothing but alpha. So we can say this is alpha minus, so this thing we can write beta is equal to alpha divided by 1 minus alpha. So this is the relation between alpha and beta, and this is a very important relation in the analysis of transistors. Now from here we can also find, this is what we found beta with respect to alpha. Similarly we can find, if we rearrange this, we can find alpha as beta divided by 1 plus beta. So that is also another important equation or important relation. So this is the relation between alpha and beta. Now the expression for the output current, that is collector current, is our output current that we have seen previously. So once again we start from this relation, that is IE equal to IB plus IC. So this is our first equation. Now we also know that IC, that is equal to alpha IE plus ICBO. So this is our second relation. So we already know these equations. Now if we substitute the value of IE from equation 1 to equation 2, so what we get, IC is equal to alpha into IB plus IC plus ICBO. So if we rearrange it, we can take this IC in the left hand side, and accordingly by taking IC common, you can write IC is equal to 1 minus alpha. So one step I have jumped here, just try to do this, or in previous CB configuration also we have done this relation. So from there also you can see, we can write it as alpha IB plus ICBO. So IC is equal to alpha by 1 minus alpha into IB plus 1 by 1 minus alpha ICBO. Now in previous slide, what we have found, that alpha by 1 minus alpha, this is what? This is nothing but beta. So we can write IC is equal to beta IB plus ICBO divided by 1 minus alpha. So this is another important relation with respect to uh, common collector, common emitter configuration. So this is our output current IC. Now this thing, we have seen that ICEO and ICBO, how they are related. Let us try to find that. So base current, once again IB, and we have seen that IC, that is equal to beta IB plus ICBO divided by 1 minus alpha. So in previous slide that we have found. So what we can find, that emitter current IE, emitter current, that is given as IC plus IB. So IC is what? From here we can find that, let us call this thing as ICEO. So we can write it as beta IB plus ICEO plus IB. So further you can write IE, that is emitter current, that is equal to 1 plus beta IB plus ICEO. So this is another relation, and also we can say that ICEO, leakage current in CE configuration that we have seen earlier. So that is equal to ICBO divided by 1 minus alpha. So that is equal to what? 1 by 1 minus alpha. That is nothing but, say, beta equal to alpha divided by 1 minus alpha. So we can write 1 plus beta, that is equal to 1 plus alpha by 1 minus alpha. So we can write it as 1 minus alpha plus alpha divided by 1 minus alpha. So this alpha get cancelled. So 1 plus beta is equal to 1 by 1 minus alpha. So 1 minus alpha, this one we can replace as ICEO equal to ICBO divided by ICBO. This is whole thing we have to replace. So not like this, you can write it like ICEO, that is equal to 1 plus beta ICBO. So this is another very important relation. ICBO is a leakage current in the common base configuration, and that is having value very low, but beta is quite high for CEO. In common emitter configuration, beta is quite high. So 1 plus beta means, this is, say, if beta is 20, then 1 plus beta is 21. So ICBO, whatever magnitude it is having, ICO is having 21 times more magnitude than ICBO. That is a typical case when beta value is 20, but beta value can range up to 500. So ICO can be 500 times of ICBO. So this is a very important relation for CE configuration, and it plays a major role for the controlling of the leakage current in common emitter circuits. So we end here the discussion of common emitter configuration, and in next lecture we'll consider the characteristics of common emitter configuration. Thank you for being with us.